Hello and welcome again. I'm going to try and summarise Diploma Programme Physics subtopic 4.2 Travelling Waves. Well, this slide just briefly introduces the concepts of this subtopic. Basically, a wave is a way of transferring energy from one point to another, and it does this by disturbing the medium, and the wave can either, so it moves through the medium, it can either make the medium, or the wave can either move transversely through the medium or longitudinally. So in a transverse wave, the displacement of the medium is perpendicular, i.e. right angle or at 90 degrees to the direction of wave motion or the direction of energy transfer, whereas in longitudinal waves, the displacement of the motion is parallel to the direction of wave motion. So an example of a transverse wave is a water wave or a light wave, whereas an example of a longitudinal wave is a sound wave. And the speed equation, which is how fast the wave travels through the medium, is equal to v, which is the speed, equals lambda, which is the wavelength, divided by big T, which is the period, the time period, which is the same as frequency times the wavelength, which you are given in the data booklet. Now let's look how you would interpret a displacement distance graph. So we're going to continue on 4.2 travelling waves, and we're going to try and interpret displacement distance graphs for both transverse and longitudinal waves. So remember, in a transverse wave, the particle or the medium is moving perpendicular to the direction of the wave. So here we have a particle A resting on the crest of a water wave. So we have, it goes from a crest to a trough, or it could be a ripple on a pond. Now as time advances, this wave is going to move to the, let's say it's moving left to right. What's going to happen to A? Well, it's going to be displaced downwards. So if A starts at the maximum, if we then interpret this displacement distance graph and look at A's displacement as a function of time, it's going to go from a maximum to a minimum, to 0 and to a minimum, and then that way. So the particle itself is moving simple harmonically perpendicularly to the direction of wave motion. So the wave is moving to the right. And one important property of the wave, which we talked about just previously, is the wavelength, and that you can get from the displacement distance graph by measuring the distance between 2 points of the wave which are in a phase. Now for a longitudinal wave, interpreting the displacement distance graph is slightly trickier, because in this case the displacements on the y, positive displacements normally mean the particles are displaced to the right, and negative displacements means the particles are displaced to the left. So let's say this is time 0, and then with advanced time we'd have time equals 1 here, time equals 2 here. Let's see what happens to the displacement of the air particles in this case. So when I advance time, this particle that was here is now going to be it's not going to be displaced at all. It has 0 displacement, because if we read off from the y-axis, it's still at its original position. However, this particle here, if this represents all the particles' equilibrium positions, this particle now has a displacement to the right. So it's now moved to the right relative to it where it was originally. So it's going to be here. This particle reading off its displacement, it's moved to the right, and it's moved most to the right. So it will be maybe somewhere over here. This particle is also moved to the right, but not so much. So it may be over here. This particle, however, is at its equilibrium position, so it's going to be here. However, if we look at this particle here, has a negative displacement, so it's moved to the left, because negative displacements means move to the left. This particle is also moved to the left because it has a maximum negative displacement, so it's moved over here, and this one's not been moved at all. This one moves a little to the left. Now, in terms of a longitudinal wave only, you can see that these air particles are all bunched up. This is called a point of compression. And where the particles are most spread out, it's called a point of rarefaction. Now, if I was to move the wave to the right a little bit more, it's moving to the right now, you see the particles have a slightly different displacement. So let's just look where the point of compression will be moved, in this case, to the right. And the point of rarefaction would also move to the right. So basically, reading off a longitudinal wave, you have to understand that displacements of air molecules are moved to the right and left with respect to their equilibrium position. And by interpreting that, you can actually work out where points of compression and points of rarefaction are.